Hi everybody, Mrs. Pesic here. We are looking at section 5.6, which is on radical expressions and rational exponents. The objectives for this lesson are to rewrite radical expressions by using rational exponents and to simplify and evaluate radical expressions and expressions containing rational exponents. New words for you today might include index and rational exponent. You should be familiar with finding the square root of a number. And so, for example, 5 and negative 5 are square roots of 25 because 5 squared equals 25. But because when you square negative 5, you also get 25 because negative 5 times negative 5 is equal to 25. That means 25 really has two square roots, 5 and negative 5. All right, these two operations are inverses of each other. Similarly, there are roots that correspond to larger powers. So let's take a look at an example here. So squaring and taking the square root are inverses of each other. But so is cubing and taking the cube root. So we can say 2 is the cube root of 8 because 2 cubed is equal to 8. We could say that 2 and negative 2 are fourth roots of 16 because 2 to the fourth equals 16 and because negative 2 raised to the fourth is equal to 16. In general, we can say that a is the nth root of b if a raised to the n is equal to b. The nth root of a real number a can be written as the radical expression, written like this, with the radical symbol, a little number here in the kind of the crook of the radical symbol, that's called the index, and the number you're taking the radical of, called the radicand, is underneath the radical. So nth root of a is how we would read this. N is the index. The plural, by the way, is indices, so we would not say indexes, we would say indices. And a is called the radicand. That's the number underneath the radical sign. When a number has more than one root, the radical sign indicates only the principal or positive square root. So on the last page we said that 25 has two square roots, 5 and negative 5, but once we write this symbol over the 25, then there's only one correct answer, and that's 5, because this radical symbol, this radical symbol right here is saying just take the principal square root. So in other words, we would only have one answer once we write it under a radical sign. Okay, so let's take a look at this. This is talking about the numbers and the types of real roots. So for example, if we have an odd index, remember the index is this number right here in the crook of the radical sign. If it's an odd number and then there's only one real root. So for example, the cube root of 8 is equal to 2. Cube root of 8 equals 2. That's the only number possible. By the way, the cube root of negative 8 is possible. That answer is going to be negative 2. Why? Because negative 2 cubed, right? That's negative 2 times negative 2 times negative 2 is equal to negative 8. What about if there's an even index with a positive radicand? That means there's going to be two real roots. So the real fourth roots of 16 are positive 2 and negative 2. All right, but remember, once I write the radical sign over the 16 and write it like this, fourth root of 16, now I can only have one answer, and that's going to be positive 2. If there's an even index and a negative radicand, then there's going to be no real roots. So for example, I can't take the square root of negative 16 or the fourth root of negative 16. That's not possible. So I'll say no answer for that one. All right, and lastly, what if the radicand is 0? Well, then there's one root of 0. For example, the cube root of 0 is 0. The square root of 0 is 0, and so on. By the way, when a radical sign shows no index, it represents a square root. So, for example, if I write a radical sign over 64, that really means the square root. So I could put a 2 there, but that's like never done. So we'll just write square root of 64 is 8. All right, so example 1, finding real roots. So let's take a look at this. Find all the real roots. What about the sixth roots of 64? Notice we're just talking about the sixth roots. We're not writing a radical sign. That means there really are two possibilities, 2 and -2. Why? Because 2 to the sixth is equal to 64, and -2 to the sixth is equal to 64. By the way, I hope I remembered to give you the list of the powers, a sample list of the powers, so hopefully that will help you as we go through this. Cube roots of -216. Well, the cube root of -216, there's only one possible answer, and that's -6. Why is the cube root of -216 equal to -6? Because -6, when raised to the third power, gives you -216. Check it on your handy sheet of powers. All right. What about the fourth root of -1024? Fourth roots, again, if I don't write the symbol, fourth root of -1024, then I would actually say there's no answer to that, because I can't have an even index here and a negative number here. That's a recipe for no answer. All right. What about the cube roots of 125? Well, there's only one possible answer for that, and that is 5, because we would write cube root of 125. It's going to be equal to 5 because 5 cubed equals 125. Okay, so let's take a look at some properties of nth roots. First of all, there is the product property of roots. For example, the nth root of a product is equal to the product of the nth roots. So if we wanted to evaluate cube root of 16, for example, that's going to be cube root of 8 times cube root of 2, and that's going to equal 2 times the cube root of 2. In algebraic terms, we would say nth root of a times b is equal to the nth root of a times the nth root of b. It's okay to pull those radicals apart. The quotient property of roots, it says if you're dividing two numbers underneath a radical sign, it's okay to split them up and write them as two separate radicals like this. So square root of 25/16 is going to be equal to square root of 25 divided by square root of 16. And then we can evaluate each of those separately and get 5/4. In general, nth root of a over b is equal to the nth root of a divided by nth root of b. By the way, before I go on to this, that does not work with addition or subtraction. You can't say, oh, square root of a plus b is equal to square root of a plus square root of b. That just does not work. Don't try that with addition or subtraction, but it does work with multiplication, as we see here, and with division. All right? Okay, moving on. Remember, when an expression contains a radical in the denominator, you must rationalize the denominator. All right, and we're going to look at some examples of how to do that, but we don't want to have any radicals in our denominator. So let's take a look at some simplifying radical expressions. Simplify each expression, assume that all variables are positive. So for this problem right here, we're going to split this up, because that's using our property that we just talked about. We can split this up into 4th root of 81 times 4th root of x to the 12th. Well, what is 4th root of 81? Check your list of powers. Is 81 a perfect fourth? Yes, it is. And it is the third number down in that list. So the 4th root of 81 is equal to 3. And what about splitting up 4th root of x to the 12th? Let's split that up into 4th root of x to the 4th times, well, let's see. Let me write it this way. Isn't it okay to write x to the 4th times x to the 4th times x to the 4th? If I multiply those out, I'll be adding the exponents, and I'll end up getting 12. But that means I can split this up into 4th root of x to the 4th times 4th root of x to the 4th times 4th root of x to the 4th. And each one of these, the index matches the exponent, so they're kind of canceling each other out. Just like the square root of something squared, the square rooting and the squaring cancel each other out. Same thing here. 4th rooting and raising something to the 4th cancel each other out. So that's just equal to x. This is just equal to x. This is just equal to x. So our final answer, don't forget about this 3 here, our final answer is going to be 3 times x times x times x. So this is going to be 3x cubed. Let's take a look at another example. What about this one? If we want to simplify 4th root of 16x to the 8th over 5, remember we can split this up and we can write as 4th root of 16 times 4th root of x to the 8th divided by 4th root of 5. I hope you're getting this example down in your notes. And then 4th root of 16 is just equal to, is 16 on our list of perfect fourths? It is, and it's the second one down, so our answer is 2 for that. And what about 4th root of x to the 8th? We could split that up into 4th root of x to the 4th times 4th root of x to the 4th, and then each one of those is going to be equal to x. So far in our numerator we have 2 times x squared. In our denominator we still have this 4th root of 5. Remember, we cannot leave a radical in the denominator, so we have to get rid of that. What I'm going to suggest to you is, before you decide what is going to go here and here, when you're going to multiply this radical fraction by something, keep in mind what you want to end up with. All right, what we want to end up with is a perfect what? We want to end up with a perfect fourth here. All right, so you're going to look at your list and you're going to say, what number is in my list of perfect fourths? So check out that little half sheet I gave you. What would be a perfect fourth, but it has to be something that 5 divides into? Well, I hope that you're getting the idea that the perfect fourth that we would want is going to be 625. So let me get rid of this. Oops. Cut. So we want to end up here with 4th root of 625. All right, we don't want to pick 16 because 5 doesn't go into 16. We don't want to pick 81 because 5 doesn't go into 81. So we're going to pick 625. But now we got to say, well, how do I get there? Well, 5 times what gives me 625? Well, the answer is 125. You could do that on your calculator to figure that out. So we want to multiply top and bottom by 4th root of 125. And so when we do this, we end up getting, let's see, 2x squared times the 4th root of 125 over the 4th root of 625. And we worked so hard to get that because the 4th root of 625 is really just equal to 5. So our final answer for this problem is 2x squared times the 4th root of 125 over 5. Can we divide out this 5 here with this 125 here like this? No, because this number is not under a radical and this number is under a radical, so we can't mix those up. No good. So this really is our final answer right here. All right, let's try this one. This one is cubed root of x to the 7th times cubed root of x squared. Let's go ahead and multiply. Since we're multiplying here, it's not addition, it's a multiplication here. We can multiply those together under the radical. So we have x to the 7th times x squared. That's going to be x to the what? Is it x to the 9th or x to the 14th? Well, when you're multiplying two numbers with the same base, you add those exponents. So it's really 7 plus 2. That gives me x to the 9th. And just like we were doing in the previous examples, let's split that up into bundles of 3's because that's our index. And I've got cubed root of cubed root of x to the 3rd times cubed root of x to the 3rd times cubed root of x to the 3rd. Each of these is just equal to x. Why are they equal to x? Because the index matches the exponent, so they're canceling each other out. All right, so our bottom line here is this is equal to x cubed. All right, and time for a notes must do. Notes must do number 1 is actually two problems for you. I would like you to simplify the expression and assume that all variables are positive. So you're going to start with this one, 4th root of 16x to the 4th, simplify that, and then 4th root of x to the 8th over 3. And remember, you're going to have to multiply top and bottom in this one to get rid of that radical in the denominator, just like we did here in this example. So I want to see what you're going to choose to multiply by. Keep in mind, you're looking for a perfect fourth, but it's got to be one that 3 divides into. All right, when you're done with that, go on with this video. Okay, so a rational exponent is an exponent that can be expressed as m over n, where m and n are integers and n is not allowed to be 0. So in other words, in this section, we're going to be looking at exponents that are not just integers, like, oh, 2 to the 5th or 5 to the negative 2nd. In this time, our exponents can be fractions. So let's take a look. The exponent 1 over n indicates the nth root. So, for example, if we have 16 to the 1/4, we would write that as 4th root of 16, and that's equal to 2. So notice, 16 raised to a fractional exponent, 1/4, this number right here, this denominator, becomes the index on the radical. All right, and this number is our radicand. All right, so 16 to the 1/4 is equal to the 4th root of 16. Let's try this with, how about 25 to the 1/2? Well, then we would write that as the square root of 25. Remember, we don't have to write this 2 here. It's understood to be a 2, and that's just equal to 5. All right, whereas this one was equal to 2. So in general, if we have a to the 1 over n, that's equal to the nth root of a. What if we have a number in the numerator of our exponent? So the exponent m over n indicates the nth root raised to the m power. So for example, we see here that we have 8 to the 2/3 is equal to the cubed root of 8 squared. Notice that the denominator became the index of the radical. All right, and the numerator just was another power outside of the radical. All right, so 8 to the 2/3 is equal to the cubed root of 8 squared, but cubed root of 8 is that's just equal to 2, and so we have 2 squared, which gives us 4. In general then, a to the m over n is the nth root of a raised to the m, or you could put that m power underneath the radical if you'd like. All right, so the denominator of a rational exponent becomes the index of the radical. All right, let's take a look at this example. Writing expressions in radical form. Write this expression, negative 32 raised to the 3/5 in radical form, and then simplify. So remember, the denominator of your exponent becomes the index on the radical. The base that you had becomes the radicand, and we're going to raise that to the numerator power, like this. That's how you'd rewrite this in radical form. Can we simplify it? Sure. We're going to look at our list of perfect powers, and 5th root of negative 32, is negative 32 a perfect 5th? Yes, it is. And since it's negative, we would get a negative 2 raised to the 3rd, and that is going to equal negative 8. All right. And how about this one? Write the expression 64 to the 1/3 in radical form and simplify. Again, the denominator becomes the index on the radical. The base becomes the radicand, and really we just have it raised to the 1st. You don't have to put that 1 down if you don't want to. So cubed root of 64, check your list of perfect cubes. Is 64 there? Yes, it is. How far down is it? It's the 4th one down. So our answer is cubed root of 64 is equal to 4. All right, time for your next notes must do. Write the expression 625 raised to the 3/4 in radical form and simplify it. When you are done with that problem, continue with the rest of these notes. All right, example 4, writing expressions by using rational exponents. Write each expression by using rational exponents. We have the the 8th root of 13 to the 4th. This time we're going the other direction. Now, what would this be as a base raised to a fraction? I need something over something here as my exponent. And this would end up being 16 to the, this number is going to go right here. And of course, the index becomes the denominator, so that's going to go right here. So I get 13 to the 4/8. But of course, 4/8 is equal to 1/2, so I can rewrite this as 13 to the 1/2. All right, what about the 5th root of 13 raised to the 15th power? Base is 13, and the 15 becomes my numerator, the 5 becomes my denominator. So I have 13 raised to the 15/5, which would be 13 to the 3rd. Okay, rational exponents have the same properties as integer exponents. So I'm just going to kind of go over these quickly. For all non-zero real numbers a and b and rational numbers m and n, if you want to multiply two numbers with the same base, what do? You add the powers. So 12 to the 1/2 times 12 to the 3/2 would be 12 to the 1/2 plus 3/2. That's 4/2, which is 2. All right, same thing if you're dividing. If you're dividing two numbers with the same base, what do you do with the exponents? You subtract. All right, that property is written here. What about if you're raising a power to a power, like 8 to the 2/3 raised to the 3rd? If you're raising a power to a power, then you are going to multiply. So we get 2/3 times 3 is just 2. We would get 8 to the 2nd power is 64. What about power of a product property? That is, if you're multiplying two numbers together and they're raised to some power, you got to multiply each one separately. Notice this is a multiplication symbol here. It does not work like this with addition and subtraction. It's got to be multiplication there. So if you're multiplying two things together, you're going to split it up and write each one separately raised to that power. All right, same thing if you are dividing two things raised to a power. You're going to take the numerator to that power over the denominator raised to that power. All right, let's take a look at example 5, simplifying expressions with rational exponents. Simplify each expression. So for this problem, we've got 7 to the 7/9 times 7 to the 11/9. I get 7 to the 18/9. If I'm adding 7/9 plus 11/9, that gives me 7 to the 2nd, because 18 over 9 is 2. All right, and that gives me 49 as an answer. How about over here? This is going to be 16 to the 3/4 minus 5/4, because I'm dividing two numbers with the same base. So that's going to be 16 to the negative 2/4. That's 16 to the negative 1/2 if I reduce. And remember, what do negative exponents mean? It means 1 over the same base, but to the positive exponent. So that's equal to 1 over 16 to the 1/2. Which is 1 over, remember we would write that as the square root of 16. This index here, or this denominator becomes the index, but I don't really need to write a square root. And then my final answer then would be 1/4, because the square root of 16 is 4. All right, that's it for this video. I hope you took good notes, got all your notes must-dos done, and you may have another video to watch on 5.8, and have a great day.